Yes, ma'am. I'll
You
just
can
share and you
start,
can.
sir. Right,
Yes.
sir.
Yeah. Welcome everyone to the day 5 on the FDP course on Foundations of Machine Learning and Deep Learning. So today we'll start into something called as deep learning, which is a bit different from all the machine learning algorithms. Fundamentally, because these type of algorithms are inspired from the how the neural networks in our human minds are connected. So these are also called as artificial neural networks. So the term deep learning is just a synonym for artificial neural networks. People just didn't use the word. I'll tell you why they shifted to this word deep learning in the later slides. So everything that you remember from all the last week till last week algorithm, those are all under machine learning. Even deep learning is a part of machine learning. It's just that it is a particular type of algorithms which deal with neural networks. And if you guys remember logistic regression, you will see again logistic regression coming today. And the fundamental unit of neural networks is very similar to how logistic regression works, but obviously added there are a few differences and changes to that. So let's get started. So as usual, a quick recap because it's been already four classes. So this is what a classification task look like, where all your goal is to try to get a decision boundary or a hyperplane that separates the classes. In regression, what we saw is we are trying to find a line or the best fit line that can describe your data. This is what we saw yesterday. So these are all the algorithms that we saw till date: k-nearest neighbors, logistic regression, naive Bayes, decision trees, SVC, support vector classification, support vector regression. Then we saw ensemble methods, regressions, and k-means algorithm. So today let's move on to deep learning. Like I said in the first class also, deep learning is the subset of machine learning, which itself is a subset of artificial intelligence. Very important to know these differences because these are the things. If you don't know these differences, it will be very unhelpful for you whenever someone asks you questions related to AI and all, because these are fundamental questions. So before even going to this neural networks, let us little bit talk about how does field itself came around, so that you'll understand why logistic regression or something called as perceptron is very relevant even for today's deep learning era. So the first electronic brain, or that's what the people call it, was first discussed or published in 1943, and then came a very interesting algorithm called a perceptron. Today we'll talk about it. So this was the very first time something called as artificial neural network was proposed. They proposed a very simple algorithm, perceptron. It was just like one node, that's it. In our entire neural network there'll be multiple nodes. In today's time there'll be like thousands and thousands of nodes, but back when it was proposed in 1957 it was just a very simple node. But the operations even till date kind of remains the same with a little bit changes. So it was back then when perceptron was published, and then within 3 years there was a variant called adeline, which is a small improvement on perceptron. And then as soon as adeline was published, for the next 10 years or so, 9 years, it was called the golden age of AI, or deep learning. For that reason, back then it was not called deep learning, it was called as AI itself. So it was called the golden age of artificial intelligence, because a lot of funding was done and a lot of people were very impressed by the way these algorithms performed and everything. Then in 1969 there was a professor, his name is on the bottom, M. Minsky and S. Papert. They came up with this XOR problem, which completely showed that these Adeline or perceptron are useless in complicated situations. Previously, people were thinking Adeline or perceptron is the way to go to solve any artificial intelligence problem. But with this particular XOR problem, they realized that no, this is not the case. And then from there onwards, for the next 10 to 16 years, it is called the dark age or AI winter, where no one even published a single paper. If you're a researcher going to a conference with a AI perceptron based paper or Adeline paper or neural networks paper, no one was going to accept or even consider you seriously. So it was very problematic back then to even talk about AI for the 16 years, and research funding and all was very low. So because of this bad name, right, people didn't want to use the artificial neural networks term again when it came back later. So that is the reason people changed the name and went to something called as deep learning. The reason behind deep learning I'll explain when we talk about the algorithms. But the reason that they didn't want to call it artificial neural networks was because this entire period where it was not well treated or it had a bad reputation. So that is why it's called as deep learning. And then in 1956 came the first multi-layer perceptron algorithm along with backpropagation. Till today, people still use these, and we'll discuss this algorithm, both what is a multi-layer perceptron and what is a backpropagation. Even all your state-of-the-art neural networks today, which you see, your big chat GPT and all, they all are based on this backpropagation algorithm, and obviously a slightly advanced versions of multi-layer perceptron. But backpropagation is a very important algorithm, which we'll discuss in detail with all the derivations and all. Then comes in 1995 SVM. So, like I said, SVM was very popular in your late 90s and 2010 till 2010. So, SVM was very popular and everyone was using SVM because while deep learning or the multi-layer perceptron was published in 1986, the problem was there was no enough GPUs. So the computation wise it was very slow. So to do very simple tasks also, like identifying digits or from an image, very simple task, even that used to take days and days of training. So there was no GPUs back then. So that is why people thought, while it is good that there is an algorithm like this, it is not realistic because it used to take a lot of time. But SVM was very popular because of the kernel trick, which we discussed yesterday. So because of that, the computation was very less compared to these multi-layer perceptrons or neural networks. And then people started using SVMs a lot. Then around 2000, late 2010s, around 2007 or 8, then GPU started picking up, and then people also had more and more data. And I think the first algorithm that showed the true nature or the power of neural networks came out in 2013. And that is where from then onwards, I think, honestly, it's not even been 10 years, it's not even been more than 11 years or something, not even more than 15 years. But in the last 10 years the entire field has completely changed. They started off with very simple neural networks, and today we have very big like trillion parameter networks also. So you can see how much research has been done in the last 10 years, because before that nothing much was there for neural networks. It was mostly SVM based. So it's always interesting to know this history, especially for a person who's just joining, to know that all the ideas, most of the ideas which today you see, these are not something that just came out now. It was there since almost half a century previously. Okay, so let's look at the first algorithm, perceptron. So I had this image kept because perceptron is very similar to how babies learn. It's something called as trial and error, where, if, for example, if a baby is looking at a toy car and a baby is looking at a doll, you obviously initially the baby has no idea. So baby might make mistakes on classifying what is a doll and what is a car, and then eventually by trial and error, by telling it that this is a car, this is a doll, it will keep on learning. So perceptron is also a very rule feedback loop system or trial and error based system, where it will make a prediction, you'll tell whether it's correct or wrong, and based on that feedback it will again improve its network or weights. So let's, as usual, we'll start off very simple. If you have any questions or anything, just stop me at any time and you can ask me. So yeah, as usual, we'll start off with a very simple, intuitive way of understanding the algorithm, and then we'll go deeper. So perceptron algorithm has something called, which is like the logistic regression. It has weights which are multiplied with your input features. So initially you have random weights. Then second step is you make your predictions, and third step is you learn from your mistakes, where you calculate error and tell, okay, what is wrongly predicted, what is correctly predicted, and then you keep on repeating the process until you get an optimal weight. So this is another example where you can think of perceptron being used to classify these fruits, right? And maybe let's just say you have green apples and red apples. So obviously initially the conveyor belt will, if for the algorithm itself, it might be picking up wrong apples. Then you will tell it, ki, okay, these are all these are all green apples and they should go into one bin. These are all red apples, I should go in the second bin. So in that way, neural networks can be used to make decisions and all in today's world. So yeah, this is more explanation about the previous algorithm itself. I'll just skip it because it's very simple. You can just read it on your own. Let's go to the actual algorithm itself. So as usual, perceptron, what is it doing under in the underlying nature? It is trying to build this classifier. It's doing the same thing what machine learning algorithms do, trying to build a decision boundary or a classifier that separates these two classes. How will it do? It will use this equation. So let's assume, let's go slowly one by one. So this particular yellow color block is a operation block, you can call. The green color blocks are all your inputs. Each input has its associated weight. So x1 has its associated weight w1, x2 w2, x3 w3, x4 w4. It's actually x2, x3, and x4. There's a error in this. So all of them are multiplied and summed together. This is what your standard up till now you saw for even logistic regression, where they multiply together and then you sum all those terms along with the bias term. Now this particular value, after summing and adding bias, you'll get two values more or less by sending into the activation function. So what is an activation function? Let's look at it on the bottom. So if your f of x value, which is this equation, and if it's very high, very positive, so it is beyond this particular vertical line, so it's on the right side to the vertical line. So maybe I'll just show. Yeah. So let's assume this is your axis. So this is your 0 0, and this is your x, and this is your y. So if f of x is greater than 0, which is all this side, then your f of x is 1. This is the activation function. This is the output which it is saying, right? So here, instead of x, I will probably change it. Yeah. Instead of x, this is basically your summation of wi xi plus that bias term. So this is on your x-axis, this value, and y. Oh, sorry, my bad. This is your x value, and on the y is your wi xi plus b. So whenever your values are x values and all, basically if your f of x value is greater than 1, then it f of x value is if wx plus b is greater than 0, then your f of x value will be 1. Similarly, if wx plus b is less than 0, your f of x value will be 0. So this is a very simple activation function that was proposed for perceptron. Let's look at it in terms of the classifier itself. So if you look at the classifier, so this particular step function which will help you create your classes, right? The output of which we call the predicted value. So based on these input values, your step function will predict either like I said, +1 or -1. You can either have +1, -1, or you can just shift that unit step. So if your step function is like this, so it is +1, -1, or you can also shift it a bit upwards. You can make it 1 and 0. So you can choose whatever you want to do, but usually people in perceptron at least use +1 and -1. We'll see a reason for that also. So they use this type of unit step function, and based on these values, your +1 and -1 comes, and this equation is nothing but this particular formula, theta I xi, for all the input features. So this is nothing but a straight line equation, right? So if you just imagine I to be just one value, then it will be nothing but y is equals to mx, obviously some bias c. So that is why you get a straight line. How much in the complexity over here is basically it's in multiple dimensions. Otherwise, this can simply be a straight line. That is why you see a straight linear classifier. So very simple algorithm, but the beauty or the reason why this was very powerful was of its update rule, and it also came up with a convergence proof. Like what it said is, if two if your data is linearly separable, like if your two classes are linearly separable means something that can be separated with a hyperplane or a linear classifier. If your data is linearly separable, perceptron will always come to an optimal w value or theta value. So that is a very good proof, which is very much needed in today's world. Today, deep learning doesn't guarantee that convergence, but perceptron back in 1957, they were able to guarantee that if your data is linearly separable, then definitely perceptron, how much ever time it takes, it will definitely converge to the optimal value. So that is why it was very powerful, and it was very successfully used for almost a decade. Let's look at how the weights are updated now. So as you can see from the figure, your input values are multiplied with the weight values. You have your summation, you have your threshold function, then you predict something. Based on that prediction, you compare it with your ground truth value, you know how much is the error, and then you back propagate that error, or you send that error backwards and update these weight values. So this is the pipeline or the training methodology of perceptron algorithm. Now let's look at in terms of equations itself. So these are all very important. So please stop whenever you don't understand any equations, because today all these multi-layer perceptron artificial neural networks, all of them are built on these perceptron equations itself. So just stop me wherever you're not understanding any equation or anything that is not clear. Okay, great. So here we see these are all the input values. So bias is not an input, but since anyways you add a bias term, we just consider that to be with the input layer, but it is not a part of input. It's just a separate thing other than input. So you multiply all these terms, wi xi plus the bias term. This is, maybe I'll just write it down. So here it should not be w1 actually. This is wrong. So it should just be 1 here instead. So from here it should be w1. This should be w2. So on to wn. So that's when you get this equation. B plus wi into xi summation from I is equal to 1 to n. Now, based on this value, if you remember the graph, your z is on the x-axis, your f of z is on the y-axis. Then you have the threshold function, which is your simple unit function. So here it is -1, here it is +1. So the greater the z, or z greater than 0 is this side, will predict +1. Z less than 0 is this side, will predict -1. So you just have two simple classes, -1 and +1. Now you have your ground truth value, you calculate the error. The error is also very simple. It's just literally just subtraction. There's nothing else in the error. So once you get that error, you multiply with something called as the gradient of this loss. So what is the gradient? Let's calculate. So what is y hat? Y hat is nothing but b plus summation of wi xi. Okay, this is your error. Now if I calculate the gradient of the error with respect to, let's just say, wi, then what will happen? First term, the gradient will go to 0. There is no dependency on w. Oh, okay. Before that, I'm assuming everyone is familiar with basic differentiation, right? Partial differentiation and basic differentiation. If is anyone that is unclear with it? Okay, so great. So if everyone knows basic partial differentiation, then we can go ahead. So the first term will go to 0. Similarly, the second term will also go to 0. All that you'll get is this wi term. So the gradient of uh, sorry, the gradient will be nothing but wi will get differentiation, and all that is left is xi. So xi into the error. So this will be your gradient, which is this particular value. So you multiply your, I'll tell you what is this eta term. Eta term comes error. So your gradient is error into xk. And now with this particular gradient of w, you update your weight. So this is how your weight update happens. W of k plus 1 is the next weight, time step weight, is equals to the current time step weight, which is wk, plus the gradient of the weight. So this term eta for now, just we call it learning rate, this particular term. We call it learning rate. But I'll tell you what exactly is learning rate when we come to gradient descent algorithm. Okay. So this is how simple this algorithm works. So let's look at the pseudo code, or the entire algorithm itself when you write it. So it's very simple algorithm. You input have your labels in positive labels and negative labels. You initialize W randomly, and then while convergence, because like I said, this convergence is possible in perceptron. So while you get convergence, you randomly pick samples from this positive from this entire data set, both positive and negative. So if your x is a positive class, you update w to be w plus x. If your x is from a negative class, and obviously you're making an error over here. Okay, let me just write that down. So here, this means negative, right? So your prediction is negative. Here, this prediction is positive. So if your ground truth is positive, but your prediction is negative, then means you're making an error. And how will you improve your weights when you make an error? You improve your weights by just adding w plus x. Similarly, if your input is negative, but your predicted value is positive, then you improve your weights by just subtracting w is equal to w minus x. That's what we got from the previous gradient, right? So here the gradient, if you see, so this is no error, it's just x. So there is no error over here. So all you get is the value of x, and based on your particular positive class or negative class, that will become w minus x or w plus x. So is this clear, the entire derivation? I know I'm going a bit fast because there's a lot of content to cover, but any doubts anywhere, you can just stop and ask. Okay, I'll always share the slide. Please let me know if you go through the slides today and ask. You can ask me tomorrow also. So this is how a simple update rule happens. So if you don't understand the derivations, all you have to remember is this diagram. This diagram. Just take away from this entire perceptron is this diagram. What does this diagram say? You have your inputs, you have your weights, you're multiplying them. Uh, yeah, is there a question? Okay. So you're multiplying both of them together and summing up together to get this net input function. Then you're passing it through a threshold function. Then you're getting a predicted value as an output. You calculate how much the predicted value is close or far away from the ground truth value. That is called your error. Then you, with the help of the error, you calculate your gradients and update your weights. Just take away this entire training loop, and that is fine. Even if you don't understand math for now, just understand this training loop. Okay. So let's go ahead. Now let's see a simple question. Let's see how much you understood. So the first one is a simple AND gate where this is your data. Its input are to I1 and I2 impulses. Your input is, if your input is 0 and 0, it is 0 output. That's a typical AND gate. Similarly, it's only 1 when both of the inputs are 1. And for OR gate, this is the second data set. Your 0 and 0, your output is 0. It's only 1 when either of them are 1. And for XOR, it is opposite, not opposite. For XOR, when both are 0, it is 0. When both are 1, it is 0. And it is 1 when either of them are 1. So this is your AND or an XOR gate. Now, can you tell me, we know that perceptron classifies AND and OR gate. What do you think perceptron, can it make these two lines? Remember, perceptron can make a straight line, right? Perceptron equation allows us to make a straight line or a linear classifier. But can perceptron make these two lines? Any guesses? I've already hinted this at the starting. Any guess? Do you think from the equation which you saw for perceptron, the simple straight line equation, this is the equation, right? The straight line equation. Do you think that two lines can be formed, or it's not possible? This case is not possible. Only these two are possible from perceptron. Okay, so the answer is no, it can't work. So, okay, this is the reason why the perceptron failed. I was telling you right in the start. After 1969, perceptrons failed because of this XOR problem. I forgot the name. The person who came up with this problem showed that perceptrons are very good at just creating a linear classifier. This is not a linear classifier because you have two lines, so it is a non-linear classifier. Linear classifier doesn't allow you to have such complex decision boundaries, since you have a complex decision boundary here which can never be possible by perceptron. So he posed this simple problem to perceptron, and perceptron never converged actually. So because of that, they came to know that perceptron can only build linear classifiers. So that led to the downfall of perceptron. But then people saw the potential and the problem where perceptron failed and how it can be improved with the help of this multi-layer perceptron. So it's like I said, all you have to remember from the perceptron was this: x1s are the input, x1, x2, x3. You multiply it with the weights, and then you have a threshold function. The only problem was this threshold function, which made this linear classifiers. I'll tell you why. So a simple example of multi-layer perceptrons: imagine you have each node, right? Each node is a perceptron. So it is called multi-layer perceptron because you combine a bunch of these perceptrons together. So that is what is called as multi-layer perceptron. Literally, there's nothing new in that word. You just combine bunch of perceptrons and they're called multi-layer perceptrons. Only difference is the activation, this threshold function, which we also call as activation function. It is slightly different. Why is it different? We'll see in the coming slides. So you can think of multi-layer perceptron like a group of experts. Each expert is your perceptron. Now, the layers of expertise, basically, you have three different layers in your multi-layer perceptron. Your input layer, where you send your data. Your hidden layers are all the layers in between your input and the final layer, which is your output layer. And then, like I said, output layer is where you make a decision or you predict a class or whatever prediction you want to do. So in figure, you see the first one is your input layer, the last one is your output layer, and everything in between is your hidden layer. So this is the terminology for multi-layer perceptron. Yeah. So this is again a multi-layer perceptron, but a very simple form of it. So for you to understand, so there's only one hidden layer in between, and the output layer basically after each particular node corresponds to a particular class kind of thing you can assume, and then based on that you make your final prediction. Whichever has the highest output at this node, we'll talk about that in a bit detail. Whichever has the highest output at whichever particular class, that will be your final prediction. And the input is connected to the hidden layer with a bunch of these arrow marks. We call it the weight connections. So previously we had just input to connecting to one node, but now that input will connect to two nodes. This is the first perceptron, this is the second perceptron. So now the number of weights will be more. Previously we had lesser weights. So this is why you see nowadays big and big models, right? Because they create bigger and bigger connections. All of the connections that they make are like this. This is still a very small. In real world, I think these what do you say, chat GPT based algorithms, right, which are GPT-4, I think even GPT-4o1 came yesterday. So those are all like billions of connections. So you can assume each of this connection as a weight. So like these connections, they have billions and billions of connections. Obviously it is not a simple architecture like this, it's a bit more complicated architecture, but connections remain the same. So you can imagine each connection to be a weight. It's just that for these advanced model, the connections are made in a different way. Okay. So let's look back at the perceptron. So like I said, this was the flow of the perceptron to make a prediction. The only problem which people found out, one of the problems which people found out was this activation function, which was a simple uh, +1 -1 function. It was not creating any non-linearity. That is the problem. Because it was just a simple +1 -1 function, the model was just creating a simple linear classifier. So to overcome that, to create more non-linear classifiers, people then went to different activation functions. They said, why just stop at a simple threshold function? So what was there previously was, so previously we had this, a simple threshold function, +1 -1. Instead, people said, let's go to complicated functions. Sigmoid you already saw. You saw in your logistic regression. That's why I said sigmoid was one of the very popular activation. It's still popular to use in multi-layer perceptrons. So you can think of each of those perceptrons to become a logistic regression model then, if you apply sigmoid. Then you have your tanh, which is slightly different from thresholding. You have something called as ReLU function, which is again very popular. So this is the most popular in today's world, ReLU. There is some variations of ReLU called as leaky ReLU and all. It's just different ways of making the function basically. Leaky ReLU has a slightly negative values if it's less than 0, whereas ReLU has 0 when it is less than 0. So a bunch of different activations are possible in today's world. Again, this is not complete set of activations. There are a lot many activations that are possible. So with the help of these activations, you convert your simple uh, the straight line equation. When you pass it through this activation, it becomes non-linear. Now the curve can become more and more non-linear instead of just having a simple straight line. So let's see how that happens actually. So this is something called as representative power of multi-layer perceptron. Very important to understand. This is the reason why multi-layer perceptrons. Is there a question? If there's no question, everyone please unmute. Okay, thank you. So this is one of the reasons I was saying why MLPs are better than perceptrons, because of this representative power. So what does representative power do? Let's look at it. So these are your inputs. There's someone is unmuted. Is there a question that you want to ask? Okay, I've muted the participant. Please refrain from unmuting unless you have a question. Okay, so let's see. On the bottom layer, you have your inputs. Now, these are your hidden layers. There's only one hidden layer over here, this one particular node. But let's see what is happening before even going. So let's say x1 is multiplied with w1, and then I said we'll do a sigmoid. So with the help of the sigmoid, now your curve becomes something like this. Now with the help of the second sigmoid, the second hidden layer sigmoid, your curve becomes something like this. Then you subtract these two, because now you're subtracting w1 x1 because of this other input, right? Just a second. Let me just show you. Okay. So these are the w1 values, w2 values, and your bias. If you remember, what was the equation? x1 w1 plus x2 w2 plus b. Now you have to do that for x1, x2. This is nothing but your bias term, so don't worry about it. So both x1 and x2 you have to do. So when you do for the first one, you're multiplying with respect to the x1 values and x2 values. Similarly, for the second one, you have their own weights, w1, w2, and bias. You again multiply x1 and x2. Now this is after you apply sigmoid, right? This is one curve which you're getting. Now this is another curve which you get. Now when you subtract these two things, this is the curve which you get. So this is more non-linear. I'll show you how that curve is coming in the next slide. But just imagine that when you subtract these two things, you're getting a non-linear curve like this. Similarly, on the rightmost side also, if you see, these are two other hidden nodes, hidden layer nodes. This is the first sigmoid activation output. This is the second sigmoid activation output. Now, when you subtract these two, this is what you get. So you see, again, when you add this and this, you get a more complex figure like this. Finally, when you again send it to another layer with the weights and biases, this is your final output. So previously, you multi-layer perceptron was able to do just this, just a single line like this. But now with the previously perceptron was doing just a single line like this. But now multi-layer perceptron can do something complicated like this, or even more complicated in 3 dimensions also they do. Imagine this curve like this. So very complicated curves are possible with the help of multi-layer perceptrons. So let's see how these operations were happening, where I said assume that when you subtract them, this is happening. So let's look at this in detail. So imagine you have one sigmoid output and your other sigmoid output like this. When you subtract these two, look at the values. They're shifted a bit on the x-axis, right? On the bottom axis, this is less than 0, and this is slightly greater than 0. So when you subtract, all the values will get cancelled on the left side, and then the values which are there on this side will get subtracted with the 0 values, and this is the curve which you get. So just take some examples and you can subtract and see how this curve is forming over here. Similarly, when you add these two type of figures, it just compounds on each of on one top of the other, and that is why you get a complicated structure like this. So this is again a very simple classifier. In real world, even more complicated classifiers are formed because the data is much more complex and the model itself is also very big. Okay, let me quickly pause for a second. Anything unclear till now? I mean, there are no questions. I'm a bit surprised. Anything that is not clear, or is this all clear and we can move forward? Okay, great. So let's look at how this MLP is trained. If you remember, I told you there's a very popular algorithm, backpropagation algorithm, that was proposed with MLP, which till date is used in all your neural networks. So very important to understand how this backpropagation works. The training flow still remains the same. What was the training flow? You have an input layer, you have the weights, which instead of weights previously, now we have hidden layer. You have your output, you compare your predicted value with your ground truth value. This is your error, how much ever your whatever function you use. I'll show you which functions to use. This error is then sent back to different weights to update those particular connections or weights. So obviously initially you'll do very badly, so your weights are random, right? That's why you do very badly. With the help of this error or this feedback loop, you tell your weights to, okay, this much is the error, you update your weights accordingly to get less and less error. That is the entire ideology of this MLP training. A very simple feedback loop systems, nothing much. So this is the error which is popularly used for classification and multi-layer perceptron cross entropy loss. This was the same error which we used in logistic regression. The only difference is over there you we used for just two classes. Here you use it for more than two classes, but the you can still use it for more than two classes also. But the loss function looks like this. This is a normal cross entropy loss where y hat y is your predicted value yi hat is your yi is your ground truth value, yi hat is your predicted value. So it's called cross entropy because entropy is nothing but I'll just write that down. What was entropy? Entropy was minus of p log of p, right? Pi summation minus. But here the distributions were the same, pi and pi. It is cross entropy because now the distribution is different. We ideally want y hat to be as close as possible to y, but since it is not the case initially, that is why it is called as cross entropy, because both of them are different distributions. So the loss is also very high. Slowly as you train your model, the loss keeps on decreasing. It means that yi hat is getting closer to yi. Your predictions are getting closer and closer to the ground truth value. Okay. So like I said, it's again a descriptive way. So for each prediction, the multi-layer perceptron gives a probability for each category or class. Like 80% it's a cat, 20% it's a dog. The closer the probabilities are to the actual value, the multi-layer perceptron is correctly predicting, or your loss basically comes down. This is what your typical loss looks like also for a simple case. When your predicted probability is cat and the loss when actual label is cat, so it keeps on reducing because the more and more confident you are a cat, you are saying it's a cat because it's actually cat, right? The loss should keep on decreasing. So that's why when your probability goes to 1, your loss is 0. Where your probability predicted probability is close to 0, your loss is very high because the actual label is cat. But if the actual label is not cat and you're predicting it as cat, then the more confident you are about it being a cat, the higher your losses. Whereas the less confident you are about it is a cat, your loss will get smaller and smaller. So again, very intuitive, but please remember this entire idea of how this cross entropy loss is working. So this is what a typical, I wouldn't say again, realistic loss function. It is much more complicated, but still this is a complicated loss function. This is how you see the losses. Previously in logistic regression, if you remember, the loss was very simple. In logistic, sorry, in logistic regression, you had a simple loss like this, or your mean squared error, right, which is your parabola. That loss is also like this. Even logistic regression is something like this, not as smooth as this, but something like this. But now you see your multi-layer perceptrons have losses like this. So you have bunch of things called as local minima, which are these points. Then there is something called as global minima, which is your standard differential calculus terms. Then there is something called as saddle point, which is neither a minima nor a maxima. And what happens is the reason why deep learning or these neural networks are hard to train is because these number of local minimas are a lot in the loss function. So when you're trying to improve your model, your loss, you'll easily get stuck somewhere in these local minima, and you're not able to come to this global minima where you have the least loss. I'll tell you how you go about in this entire function, how you should move around. We use a standard gradient descent, which we talked about in the starting second class, but I'll again discuss that once again. But the idea or the reason why deep learnings never have this convergence proof is because you can't guarantee that your model, whatever output you're getting, it is a global minima. It could very likely be that it is a local minima, and there is no guarantee for that. So that is why we say that the convergence for deep learning is hard, or it's not hard, it's not proven basically. But on what conditions, we do have some idea about when it will do the best, but we still don't know for sure. Okay, so this was the gradient descent algorithm which we talked about, but let's again go through it once. What did gradient descent say? So all of the okay, firstly, what is this curve? This curve is the loss curve, right? How is loss coming? Let's derive it. So what is loss? Loss is nothing but, let's say for now, a simple, we'll take mean square error loss, y minus y hat square. Okay. Now, what is the y hat value itself? Y hat is nothing but w1, w into x. Let's simple case. Only one variable you have, w into x. So technically, what is loss? Loss is nothing but a parabola or a degree 2 equation, because y is a constant. This you don't have to worry, into wx whole square. Now, if you expand this, what do you get? Y square plus w square x square plus, minus 2wyx, right? So this is nothing but your loss, which is this equation which is this function which you see. This is your loss basically. So on your x-axis is your weight w, on the y-axis is your function of loss. Cost is nothing but loss. So now with respect to this loss, y w is w square, right? So it's a parabola like this. Now when you have a parabola, what do we want to know over here? Initially, w value we don't know. That is what we need to learn. W value initially is random. And over a period of time, like let's just say I've run this model for 100 steps. Over a period of time, I want this w to come over here. I want this w to come over here. Why? Because this is the minimum point that is possible for a parabola. I mean, everyone has assumed about the parabola minimum, right? Where the value, uh, that lowest point in the parabola is called the minima. And parabola doesn't have different global and local. It has just one minima, which is the global minima. So we want, after some 100 steps or 1000 steps, how many ever steps, we want the w to come here. So what did people say? Okay, let's come up with an algorithm where you initially start off here. This is your initial w value. And then over the period of these 100 time steps, each arrow is a time step. Over a period of this 100 time steps, you slowly come down and you settle at this point. You should not again go above. You should not go above. You should just settle at this point. When you settle at this point, your loss will be the lowest, and the w value will be optimal because it is corresponding to the lowest loss. And that is where y is lost lowest means w is optimal, because y is close to y hat, right? Then means you're predicting what is ground truth. So these are multiple interpretations to the same working of the algorithm. Okay, I'll quickly pause and then we can discuss how this step by step incremental update happens. But is this idea clear? How gradient descent makes w come to a point where it has low loss, which means that y is closer to y at that point. It's very intuitive. But any questions or anything that you have that is not clear in this intuition? Okay, great. So if this is clear, let's see at the algorithm itself. So this is the algorithm, a very simple algorithm which says update w such that the new w is equals to the current w minus alpha. So remember previously I told there's a term called eta, right? And I called this the learning rate. So this is your alpha over here. I'll explain what that learning rate is now. And this is your gradient with respect to w, gradient of the loss with respect to w. So simply update rule, which was very similar to our perceptron update rule also. So let's go back and see what does alpha mean over here and what does gradient mean. Okay, so gradient of a function is nothing but, if for example at this point, the initial point, what is the gradient? Gradient is nothing but this particular value, which just touches the function. So this is your gradient. And what the algorithm is saying is, you look at the negative of the gradient, which is going down. In this case, you look at the negative of the gradient and you take a step further. Now, next question is, how big of a step should I take? This is where your learning rate or alpha defines. So based on your value of alpha, that much big of a step you take. So if your alpha is very big, you take very big steps. Maybe instead of this, you take something like this. But if your alpha is small, then instead of this, you'll take something smaller like this. So based on your alpha value, you take that big of a step. So that's why people say don't use very big alpha, because if you're at this point, or if you're at this point, let's just say, and if you have a very big alpha, it'll just jump over here, which we don't want. And people say don't use very small alpha also, because then you will converge to this point very slowly. This entire, you'll take smaller and smaller and smaller steps instead of these steps. So alpha again is a hyperparameter, and you can use your validation pipeline, right, which we talked about till for hyperparameter tuning. You can use that to decide which alpha to do. So that's it. This is your gradient descent algorithm, which is very popularly used in neural networks. Obviously, there's a bit addition apart from gradient descent. There's something called as back propagation, which we'll discuss next. But I hope the gradient descent is clear. Any doubts or any questions? Okay, let's move forward. Now let's come to back propagation itself. So what does back propagation say, and how is it different from your gradient descent, and what all things do you need to understand? So before that, let's look at this perceptron figure and compare it with this particular uh, figure. Yeah. So previously in perceptron, you had just inputs and you had one node. Okay. And you multiplied the weights, you did your summation and that threshold function, and then you predicted your value y hat. And then what did I say? You update your weights, right? These are your weights: w1, w2, w3. So these are your three weights. Then you update your weights, like wi is nothing but wi minus of alpha into the gradient. For now, gradient I'm just writing like this. Okay, alpha into the gradient. So here, since there is just one node, so whenever you get that gradient, right, you can just send over here and update each of the weights. But what happens is, because the y hat is easily dependent on these w1, w2, w3 directly. But for example, let's just take the this scenario. Let's just say I have a weight w prime 1, w prime 1, and if I have w double prime 1. Okay, these are two different weights, right? Now when I'm calculating the loss, what do I calculate? Let's just take a simple difference, mean squared error loss only. So my loss is y minus y hat. Okay, now if you expand it, it will be y minus some term. Let's call it some here. uh, some extra terms are also there. We'll call it beta into w1 double prime, and there'll be some extra terms also. Okay, now if you expand this further, because this w prime is also dependent on w1, right? Then you'll get y minus w1 double prime into something like alpha, no, not alpha, I'll just use some other, gamma into w1 prime. So you see there's a lot of dependencies that are happening. So you can't simply calculate easily the gradient with respect to the inner weights. So that is the point which I'm trying to make. Calculating gradients with respect to these weights are easy, but calculating gradients with respect to these weights are harder. So now what do we do? That is where back propagation comes into picture. Back propagation is a very simple algorithm. It is just based on your chain rule of differentiation. If you remember the differentiation properly, it's just your chain rule. So this is again the same in terms of equation, which I just explained. you have your cross entropy loss, and you can just send it back with the help of backpropagation rule. So okay, sorry. Let's look at chain rule first. I know most of you are familiar, but just in case, we'll look at the chain rule and then we'll see how backpropagation applies this. So what does chain rule say? Chain rule says that if these are your dependencies, like A is equals to 2 is just starting, these are the nodes, starting nodes, and then C is dependent on A and B with A plus B, then partial differentiation of C with respect to A is 1. Similarly, partial differentiation of C with respect to B is 1. Here also D is equals to B plus 1, and partial differentiation of D with respect to B is 1, and we get the same values over here. So if you understand these partial differentiation concepts, right, then it is easier for to understand this particular thing. So if you have a function like z is equals to e to the power xy, x is 2u plus v, y is u by v. What is the differentiation of partial differentiation of z with respect to u? Remember that u is z depends on u in two ways, both x and y, both of them are there. So you first calculate your partial derivatives, your dou z by dou x into dou x by dou u plus dou z by dou y into dou y by dou u. And now you calculate what is dou z by dou x, y into e to the power x, xy. Similarly, dou x by dou u is just 2. Similarly, you calculate for the other two terms and you just multiply them. And this entire thing together is your final dou z by dou u. So this is your standard chain rule. This has nothing to do with neural networks. This is standard chain rule of calculus. I hope this is clear. So in a similar way, your weights will get multiplied now. So let's say these are the inner weights, which I'll call W inner. These are the W outer weights. So the error with respect to W outer weights are easy to calculate, which we just saw. That is very simple to calculate depending on the value whichever you have. Now the error with respect to the inner weights is dependent on the error gradient of the partial derivative with respect to outer plus some more terms. I'm just calling it gamma plus this. Just write it clearly. Sorry. Let's write it clearly. So dou E by dou inner is nothing but dou E by first outer ones into the outer ones are further dependent on some other terms in this values which you get, right, I, J, M. For now, I'm just calling it gamma into dou gamma by dou inner. You know what these values are. We can calculate it without like you don't even need to compute the output. You can just calculate it before only, right? Because if you remember this chain rule, you were able to calculate these before without even calculating the output values. So these are just the dependencies which you already know. So that is why it is beneficial. This algorithm is beneficial because most of these partial derivatives can already be calculated without even calculating the output. So you can store these values, and whenever backpropagation is called, we can immediately use these stored values. Some values needs to be inputted based on the error, but some are already existing as a dependency. So this entire thing is your chain rule, and this is how you update your weights. This is how you calculate the gradients with respect to your inner weights. And once you know this gradients, the rule is simple, right? W inner is equals to W inner minus alpha times this gradient, dou E by dou inner. So in this way, the backpropagation updates even the weights for the inner weight, even the inner weights basically. Okay, let me pause again. Any doubts? Anything that is unclear? Very important derivation. Please, even if you want me to repeat it once again, I'll repeat it because this is very important. If you didn't understand this, then there's no point of MLP training and all. Okay. Sure. Then let's move ahead if everyone is clear with this. So this is one reason, along with the activation function, why MLPs were again brought into the picture. But again, the problem over here was not yet solved until GPUs came in, because with the help of GPUs, multiple parallel processes could be done, like storing of these partial uh, derivatives were done parallelly instead of waiting for the sequential calculation of output and then going back as the error. So a bunch of things could become parallelized. So that's why GPUs were helpful to make these MLPs train faster and faster. So there are some terminologies which people use during MLP training, which is very important. The first term is called forward propagation. Like the name suggests, you're sending the data from the input and calculating the output. That is your prediction. The second is called error estimation, where you calculate the error. The third is called your back propagation, where you calculate the gradients and then send it back and update the weights. These are the three important steps in your MLP training. Even in your code, right, when you're writing the code, you will follow the same three steps, but it's much easier to write the code than understanding the theory. But the steps remains the same: forward propagation or forward pass, error calculation or error estimation, backward propagation or backward pass. Okay. Now there is something called as different variations of gradient descent, like I said. So before going into that also, let's talk a bit more about how in your real world you actually do the gradient descent. So previously, when you looked at the gradient descent algorithm, let's write it down. What was the gradient descent algorithm? Wi, new Wi is nothing but old Wi minus alpha, which is your learning rate, into your gradient. Okay. So usually for this, you use your entire data set. What I mean is that to calculate these gradients, right? You calculate the gradients for the entire data set which you have. So this is calculated over the data set, entire data set. So you calculate for each point, because here there is some xi values also, right? Some values will be there. So for each xi data point, you calculate this particular gradients and you update the weights. Now, the problem happens is in today's world, the data sets are not small. Previously, it was fine. But in today's world, the data sets are like in orders of millions, even like 500,000, like 500,000. These are all standard data sets. It's not even like complex data sets. So now when you have such big data sets, problem is you can't load this entire data set on your GPU RAM. So GPU RAM, what are the standard specifications of GPU RAM today? You have most of the laptops which come with inbuilt GPU have like 8 GB or 16 GB max to max. Now, if you go and buy something like specific to NVIDIA, specific to deep learning NVIDIA GPUs, you will get 32 GB also. You'll also get 46 GB. And there are the most powerful, one of the most powerful GPUs are A100. They come with a version of 80 GB also, and there is some H100 and all, but max to max it can go to I think 120 GB. That's it maximum. Whereas images, imagine these are 500,000 or million thousand images. Each image will easily, even if these blurest, like not blurest, but even if you take a normal low quality picture, they have 224 comma 224 pixels. Okay, and to store them, each of them takes some like 8-bit precision, 8-bit or 16 bits. Okay, so this much will take for each pixel value, then all that much value into this entire term. So it will go way beyond these 80 GBs or 32 GB or 46 GB, that into 500,000 or million. So I guess you're seeing the problem over here. So the problem is we can't load the entire data set onto your RAM. So what did people do? Okay, let's split the update then. So then the entire sending the entire data set is called as batch gradient descent. Then people said, okay, don't send the entire data set. Let's split the data sets into batches. Like batches is nothing but normal, like, groups of data. So that is what the algorithm called as mini batch came. Now, next question is like, if I have a data of 10, so what should be my mini batch size? I can either do just two, like this I'll have five, or I can do five with this I'll have two. So mini batch, this value is called the batch size, which we call in mini batch. So this batch size actually plays a very crucial role in your training, because they help your gradient descent algorithm to converge to the minima in different ways. So let's look at it. If you're doing a batch gradient descent, then your batch size is nothing. It's your entire data set. So you can quickly come in a straight line to the minima. Let me change the color. Yeah, you can quickly come in a straight line to the minima in the batch gradient descent update. Whereas if you use mini batch, so you come in a wobbly state. The smaller your mini batch, the more variance, we call it variance basically, the more up and down, up and down, up and down your curve will be to come to the optima. The worst case is this stochastic gradient where your batch size is 1. So this is your batch size. In this case, you can see how highly variant this particular optimization process is. So this type of optimization or convergence will is like, it'll take a lot of time and it is not good. Sometimes you won't even converge. But whereas ideally you want to be in batch gradient descent, but you can't be there, so you try to come to mini batch. So depending on your GPU capacity and everything, you try to have a decent amount of mini batch size for mini batch. So standard practices for that is people start off with 8 also, depending on the RAM, 16, 32, 64, 128. I've barely seen 256 and 512. Beyond this, it's very unlikely if you're using big data sets. Max to max, these are the ranges what people use in today's world. So, in fact, if you when you use your big neural networks like LLMs and all, right, large language models, you'll not even use 8. You'll use 1 or 2 because the model itself is so big, right? You have to load that entire model on the RAM first, and apart from that, you'll have to load data also. So this is why this entire concept of mini batch and stochastic gradient descent have come into picture. Okay. Again, a quick pause. Any doubts? Anything that is unclear? Why or the motivation to why is this mini batch or stochastic gradient descent is? Okay. I am audible, right? Can someone confirm?
Yes, sir.
Hello. Okay. Okay. Sure. Sure. Okay, ma'am. Yeah. Okay. Then let's move on and let's come to something called as regularization and what it means. So, if you guys remember the concept of overfitting, right, which we talked about. So, what does overfitting and regularizations are very closely linked. So, first I'll talk about that in like 1 2 seconds, and then we'll come back to regularization. So, what does overfitting do? Like, for example, if this is my data, this is one class. Then, if I have another class like this, then a situation is called overfitting when your classifier does something like this, right? If your classifier is something like this where it is trying to fit to all the possible variations that is there in the data, then this is called as overfitting scenario. Now why do such cases happen? Because what is the space when I'm doing this is nothing but your weights, right? This is w1, this is w2, so these are nothing but your weight space. These are all your weights. So when the w1 value can be uncontrollably large or uncontrolled, there's no control or restrictions or constraints on these w's, right? Then it can go whatever way it want. That is why overfitting happens. Now what is a very good way to control them? Obviously restrict their magnitude. That is what the regularization says. So let's look at this. So if this is w1 and this is w2, and if I restrict my values to just fit in this diamond of unit 1, if this is 1 minus 1 plus 1 minus 1, so if I say that w1 value and w2 value should not go beyond this particular diamond, then I'm restricting my values, weight values to a certain extent, then this type of classifier will never form because W1 can never go uncontrollably large or W2 can never go uncontrollably large that can form these unnecessary curves. It is always restricted to some extent. That is what L1 regularization does, which you see over here, right? So imagine now this particular diagram on 3 dimensions. So this is what it looks like. So you have to imagine this blue color going into the screen and the red ones are coming out of the screen. So that this 2D dimension, this 2D figure is nothing but this L1 regularization's 3D figure. Same thing if you control it using a spherical or a circle, sorry, in 2D it's a circle type of restriction, you see something like an L2 regularization. this one. So in this way, you're controlling your weight values and hence you're reducing your overfitting. There is also an difference between both. You can use L1 or L2. Some differences are there, like when you restrict your value to L1, right? People say ki most of your weight values can go to zero quickly, because when your loss curve, it usually touches at the edges. If this is your loss, it usually touches at the edges. Whereas for this, the loss can go, the loss can go, sorry, yeah, the loss can go like this. Whereas for this particular case, the loss will go like this, touching the edge. Here, it's not touching the edge, so W1 and W2 can be here also or here. Whereas since it's touching the edges, W1 will become zero. Don't worry if you don't understand the loss part of it, but at least I hope you understood how regularization helps in reducing overfitting. That is very important. Please make sure that you understood that concept. If that's not clear, please let me know, because this is very important and you need to use regularizers, any one of the regularizers, when you're training your multi-layer perceptron. Because like I said, MLPs are very complex, right? Very huge and very big. So whenever you don't know how big of a network you have to create, many people initially they create like 100 layers, which is not even needed. So when you create like 100 layers, then you have a small data, immediately it will overfit. Then people will like, what should I do? Obviously reduce the number of layers, but even after that, if it's still overfitting, then add these regularizers. So it's very important to understand how these work. Okay, apart from regularizer, there's something called as dropout. This is again used for overfitting only, to reduce overfitting. So on the left side is what your standard neural network connections are, where you connect every previous layer to every other next layer. You can see all the arrow marks are there. In dropout, it says that you randomly misplace or you randomly drop some connections between the layers. So why is this helpful? So previously, let's take a simple example. So let's say uh, after one forward pass, the prediction y hat is equals to some class dog. Okay. Now, what I don't know, or what a even MLP doesn't know for that reason, what a person doesn't know is this y hat prediction equals to dog, which is a correct prediction. Did the model actually learn the weights, or did it just memorize, or did it just by heart all what does a dog look like? It didn't learn what a dogs look like. It just learned that okay, if such particular type of a dog image is shown of this particular image, it is a dog. It just learned that. It didn't learn the patterns of a dog. So to understand that, what they say is, like for example, these are some connections, the connections which dropped, right? So let's assume that this entire cell was used while predicting whether it's a dog or not. None of these cells were helpful. It didn't use, only the neural network didn't use any of the first three cells. It just used the last particular perceptron and used that to make the decision y hat is equals to dog. It turned out to be lucky and the guess was correct. So but it doesn't mean that the network is actually learning. So to avoid this, people said you drop this entire last network itself. Now if y hat is still dog, then the model actually learned. But now if y hat is saying cat, then that previous case was overfitting, because as soon as you remove this particular node, the predictions changed. So to make the systems or the what is it, network more robust, you randomly drop so that there is no dependency of on any of these nodes to make the entire prediction. So it is forcing the network such that every particular node should learn some important feature or other about that particular input sample. So this is why dropout was very helpful. People still use all of these concepts which I'm explaining, right? These are all used in today's world, even very popular in research also. Okay. Then again, another technique to speed up training and to overcome overfitting also is batch normalization. Concept is very similar. So previously, if you remember, we had scaling, right? So if my input features, let's just say x1 was in the range of 10 to 100, and if my feature 2 was in the range of 10,000 to 1 lakh. Okay. Now I said that whenever you have such drastic or such huge difference in the scales, right, you normalize them. What you try to do is you bring them into same scale. To make the training process fast, the same concept is applied after every layer. Now these are hidden layers basically. So this is hidden layer 1, this is hidden layer 2. So now after every layer you apply this similar type of normal. So if you can see, this is of a different scale than this. Like this is scale 1, this is scale 2, and this is again scale 3. Now you want all of them to follow a similar scale, which is where you normalize all of them into this particular graph. Now, if you normalize all of them, because this H1 is acting as an input to H2, right? So it's the same concept. If your input features are not of the same scale, training is going to take a lot of time and sometimes bad also. So just have that intuition. Since H1 is an input to H2, you're normalizing all of these values before sending it to H2. That's it. So very simple concept. Again, very powerful concept. So this is how your values look like. Your original activations are on an entirely different scale, like 0 to 10. After normal, you look at the X values. After normalization, the values are in a particular range, -3 to 3. And if you do a better normalization, -4 to 4. So you're trying to scale the activation values or the outputs of the hidden layers. Okay, so maybe I'll quickly pause over here. We can talk about images tomorrow. I'll try to show some code. I know it's already 8:20, but I'll try to show some code before we end the session. Images we'll talk tomorrow when we talk about convolution neural networks. Any doubts or anything? It's okay if I'll explain it again. We can talk the code also tomorrow. But everything is clear up till what I spoke today, right? All the layers and all. Okay, great. So I'll share these collab notebooks. This was taken from one of my Professor Vineet Balasubramaniam. He teaches NPTEL course, Deep Learning for Computer Vision. In that, this assignment was created, collab notebook was created. So I've taken that because it's very good to understand everything basic about neural networks. So you can always, I'll share this. You can always look at his entire GitHub repository also to understand better. Okay. So let's, before even talking about what is a PyTorch. So previously we talked about a scikit-learn, right? Like I said, scikit-learn is a very good library to understand, to use, because it has a lot of these machine learning models already built in. It was just what, 2-3 lines you had to use, dot fit, dot predict. That's it. Now, similar to scikit-learn for machine learning, there are two popular languages for deep learning. One is PyTorch, which we'll talk today. Another is TensorFlow. So both of them help you to create neural networks in a very simple way. You, again, like how simple it was creating machine learning models with scikit-learn. It's obviously not that simple, but relatively very simple. You don't have to worry about calculating the back propagation. Don't worry about calculating gradient descent. You don't have to worry about, how do you create all small connections, weight connections, multiplications, matrix multiplications and all. Don't have to worry anything. You just have to call certain classes and functions, and your neural network will be created. So today I'll just talk about some basics of PyTorch itself. So here, this is more extensive. It has a lot of in detail operations of how PyTorch works and everything. I have a shorter version. I'll share that also with you guys. We'll do the shorter version today, and you can go through the longer version on your own time and let me know if you have questions. Okay. So a basic unit of a PyTorch is called as a tensor, which you see over here, right? This is a tensor. So tensor is like your array in NumPy. In your C, also C++, you have array, right? Basic data structure. PyTorch basic data structure is a tensor. So tensor is nothing but anything which is beyond 2 or 3 dimensions. We call it a tensor. 1 dimension is a vector, 2 dimensions is a matrix, 3 or more is called a tensor. But people nowadays, changing times, people call it one-dimensional tensor also, which is nothing but a vector. So just make sure that in today's time, mostly tensor is used for anything. So make sure you know the dimension of that tensor to know what exactly that particular is. But in actual mathematical terms, tensor is anything beyond 3 dimensions. Okay, so how do you create a tensor? You have a list of values like 1, 2, 3, 4, let's say. So this is one way to create your tensor. You just write torch.tensor and you input that particular list. So this is when you print that X, right? This is what you see, tensor 1, 2, 3, 4, 5. And then there is one command present in PyTorch that will help you know whether your particular system is GPUs available in this particular system or not. How is that possible? With this command. torch.cuda is available. So always make sure that your GPU is supported. And on Collab, that is the benefit again. Free GPUs are available on Collab. So you can always use that. Otherwise, if you have your own GPUs, make sure it is properly connected with your PyTorch. Just run this command. If CUDA is available, it will print the first thing. Otherwise, it will print the second thing. CUDA is not available running on CPU. So right now, I didn't connect my particular Collab notebook to GPU because you have to separately connect that. Maybe I'll just show you here only. So you have to go to runtime, and then there is something called as change runtime type, and then there is bunch of options. So T4 GPU is freely available. A100, like I said, no, one of the powerful GPUs that you have to pay extra money. That is like a subscription. There is other L4 GPU also. Then TPU is even more powerful. It's not powerful. It's meant for these tensor type of operations. Like it's called as a tensor processing unit. CPU is central processing unit, and GPU is graphical processing unit. TPU is tensor processing unit. So you can select particular whichever particular processor you want. Okay. So with this particular command, you now know whether your particular system is GPU supported or not. Next, let's look at some of the simple operations. So let's first thing is something called as a zero dimensional tensor, where it is just one value, scalar value, which is tensor torch.tensor of 5. This is just a scalar value, so we call a zero dimensional tensor. Then I told there's one dimensional tensor, which is a vector, you can call like this. Then there is two dimensional tensor, which is your matrix. And then there is three dimensional tensor like this, which is defined like this. And to know the shape of these particular tensors, you have this command called dot shape. So if you do scalar dot shape, then you'll get the shape of that particular tensor. Obviously for scalar, there is no size. So size is null, like 0. For other values, you have, this is a size of 4, vector of size 4, matrix of size 2 comma 3. This is three dimensional of size 2 comma 2 comma 2. Okay. Now let's do some simple operations on two different tensors. Like for example, you have this tensor A, tensor B. You can do all the basic Python and NumPy operations which you did, right? Even more are possible in PyTorch, but all of the basic ones are possible, like add two tensors, subtract two tensors, multiply two tensors. You can use the simple operators, divide two tensors. Then there is something called as reshaping. So if you want to change the size of one tensor, let's say I have the size of tensor from 2 comma 2 to 4 comma 1. So if I want to change this, I use this particular command called dot view. So the tensor a dot view, and I mention the new size 4 comma 1. So when you're using this dot view, right, make sure that the sizes are actually compatible. If your original size is 2 comma 2, you can't write 6 comma 1. You can't convert it to 6 comma 1 because the number of elements are only 4. So make sure that compatibility is there, otherwise it will throw an error. So the reshaping is done like this. Then there's something called as indexing or slicing, which is similar to your normal arrays and NumPy arrays, right? Where if you want to just get the first row and all the column values, you just write in brackets 0 comma colon. Colon means all the second dimensional values will be included. So yeah. Now let's go into some code, like actual MLP code itself. So you can always look into the other code which I told you, right? I'll say share that. It has much more detailed operations about PyTorch, about tensors. Okay, in today's first data set, we will use the same wine quality data set which we discussed yesterday, which had like I think 16 attributes and 6 classes or different classes. Yeah, is there a question? Okay, yeah, so different classes corresponding to different wine quality. These are the attributes of all the classes. Now, as usual, I think by now you're all familiar that how to load the data set and how to use train test split on the data set. And then you also scale. Yesterday talked about scaling, right? How to scale all the features using standard scalar. You can do scalar.fit transform on train data set. Don't do fit transform on test data set. Very important to know. Then you just print all the shapes of each of these just to know what you're dealing with. So the first one is 127, 11, the X train. This is the Y train, which is 127. Then you have X train, X test, which is 312, 320, 11. and then you have y test, which is just 320. Okay. Now let's create your MLP model, multi-layer perceptron model. So before that, let's look at some import statements since these are new. So the first three import statements which you see, those are new import statements which were not there yesterday or in the previous classes. These are related to PyTorch. So to import PyTorch, you first write import torch. This will basically import the PyTorch library in your environment. Then there's something called as NN library in Torch. This is short form for neural networks. So whenever you want to create a neural network, always use this particular NN library. I'll show you how. Then there is another module or class in PyTorch called Optim, which is basically short form optimizer. So whatever optimizer you want to use. So gradient descent is one optimizer, like the stochastic gradient descent or mini batch, whatever you call. But there are a lot of optimizers out in the world that is out there. So Adam optimizer, RMS prop. So there are more advanced versions than basic stochastic gradient descent. Okay. So these are the three important libraries that you download, and let's see how the class can itself be created. So you first define a class. In this case, I'm just calling it wine quality network. This is the class name I'm giving. So whenever you want to create a neural network class, always inherit this particular parent class, nn.module. This is a PyTorch class which is existing. So whenever you are writing your neural network, when you inherit this particular parent class nn.module, it will immediately tell PyTorch, okay, this particular class which is written, right, this is of a neural network type class. If you don't write this nn.module, right, then it won't detect that this particular class is a neural network. It will just ignore it like some other class. So make sure that nn.module is always inherited first. So that is important. And then there are two important functions that you have to define in a in this particular class, always important. Whenever whichever neural network you create, two important functions that you have to write or create is init function and forward function. So let's talk about the init function first. So init function, like the name suggests, it is used to initialize all of the global variables that we will be using in that entire class. So what are the global variables? Like if you want to define how many hidden layers you want, what should be the size of each hidden layer, and what should be the activation function? Do you want dropout? Do you want batch normalization? All of those things you can define in init function. In the forward function, you basically tell how the data should flow. So in the forward function, you see the input is x, and then you tell first where should the x go. The x is going to the first layer, fully connected layer. Then that x is going to the activation, which is ReLU. Then that particular output is going as an input to the second fully connected layer, and then finally that is returned. So in this way, you basically tell the PyTorch, this is how the data should flow, from which network, what activation, and then next which network, and what is the output. So this is what forward function does. Now let's look at each of these variables closely. So the first, to define a fully connected layer, you import again this particular class called nn.linear. So you don't have to worry about calculating, or doing that multiplication weights into input. You just write this nn.linear, and it will take care of everything else. All you have to mention is what is the input size. In our case, the input size is 11, and what should be the size of your hidden layer, which is 64. Now the second fully connected layer, what is the input? It is coming from the first one, right? So input size is 64, and output is just one particular value, so that is why it is 1. Okay. So ReLU is your activation function. And now after this, you define your neural network. This is a very simple multi-layer perceptron. People basically keep on increasing the number of fully connected layers. They add a bunch of different activations or a bunch of different those, what do you say, uh, functions like batch normalization, dropout, and all, and they make it more and more advanced. But this is a very simple neural network which you just created. Now let's call this model and let's see how to train this model. First thing first, you have to initialize the model. How do you initialize the model? Like you initialize any class, right? You just mention the class name, wine quality net, and then what was the input that is needed? The input that is needed is the input size. So here you mention that x train dot shape one, which is 11. So now you created an instance of your neural network in model. Next, you have to define your loss, which is your criteria. Criteria is another is also called as loss. So what is your criteria? In our case, since a regression problem, right? So we use MSE loss, mean squared error loss. Again, you don't have to worry about writing it. It is already existing in PyTorch. That is why we call nn.mse loss. So it's a very simple loss and easy to call from PyTorch. After you define your error function, you define your optimizer. Instead of gradient descent, we will use something called as Adam. Don't worry, it is a type of gradient descent only, advanced version, but the entire process remains the same. How you calculate the partial gradients and then you update the weights, all of them remains the same. It's just it's a more slightly advanced version of gradient descent. So how do you call that? With the help of this optim library in PyTorch, optim.adam. Okay. Now, the only difference is previously you didn't convert any of your data, right, into a tensor because we were using scikit-learn, and scikit-learn can take input as a numpy array. But tensor PyTorch doesn't take input as a numpy array. It takes input only tensors. So that is why you first convert all your train set and test set into tensors with this particular lines, torch.tensor, and just you can mention which is that numpy array, and all of them are converted into tensors. Now you write a small for loop. What is a small for loop? This is the number of steps I was talking, right? In how many number of steps your model should keep on updating its weight and converging to the optimal value. This is that for loop. So we call it epochs. Epochs is basically how many times you want to run your model. Don't worry for now. There is a advanced version which, if we get time, we can discuss it tomorrow, which is where you have multiple for loops. Inside this small inside for loop, you have the mini batch also, which I was explaining. In the outside for loop, you still have epochs. But for now, since the data set is small, we will just use epochs. For big data sets, we do that. Okay. So we define to run this loop for 100 epochs. That is what you're defining. Number of epochs is 100. So for each iteration, this is what your forward and backward passes will be. If you remember, there were three crucial steps, right? Forward pass, loss calculation, and backward pass. So these are the values. These are those steps. What is the forward pass? Very simple. You just call that model function which you created on the top, this model class instance. You just write model and send the input value x train tensor. You get your output. Then you already define your loss. So you just call that criteria. And what are the arguments? Your outputs, predicted values, and your ground truth values, y train. You get your loss. Second step is also done. Then finally, what is your third step? Your backward pass and weight update. So these are the three lines which you need to mention for that. First is optimizer.zero gradient. This will basically, it's like sometimes in this iteration, right? Some previous gradients from previous steps by mistakenly will be stored. So you don't want any of those. So you first zero out all the any garbage gradients. So it's very important to write this step, optimizer.zero grad. It will basically remove any unnecessary gradients from previous steps. Then you call loss dot backwards. This is where all the you tell your PyTorch, okay, we are ready for back propagation. All the partial derivatives will be calculated and partial gradients will be calculated. Then in optimizer dot step, you update the weights of all the parameters. That's it. Your simple backward pass is three lines. Your forward pass is just one line. Loss is also one line. In this way, you run the loop for 100 times. Each after every 10 times, you can print to check what is the loss value for that particular epoch. So this is how your loss looks like. So initially it was 30, obviously because it was random weights. Then after every epoch, after every 10 epochs, you keep on updating, your loss comes down to 10. Obviously, the network was very simple, so that is why you have this much loss. When you keep on doing better and bigger networks, your loss will come down even further. Okay. So this is how you can do evaluation. So there is something called as model.eval and model.train. So whenever you're doing evaluation, you set your model to model.eval. That means that it will drop off some particular things which are not needed for training, which are not needed for testing. It will switch them off. So that's why you need to always call this model.eval before evaluating. And then after you finish evaluating, you just call model.train whenever you're starting your train. So in that, you simple again, you just do a forward pass where you send your test data, you get your predictions, and then you calculate your loss with the help of your ground truth values, and that is what you print. So this is a simple regression using MLP. Classification also very similar. There's no change at all much. In First thing is you are doing it on the breast cancer data set. So you just load the data set. Let me show that. Yeah, let's look at the network itself. Network is very simple. You have your first fully connected layer like last time, two layers, one activation ReLU layer after the first hidden layer. You have one sigmoid. Why do you need this sigmoid? The sigmoid will be the output activation layer, which will basically tell whether it will basically squash the values between 0 and 1, sigmoid. So it will tell whether if it's close to 1, it means it's a cancer class, or if it's close to 0, it means it's not a cancer class. So that is why, since it's a classification, you have an external extra activation at the end of the output. So the forward function again remains the same. You tell the data, go first to the fully connected ReLU, then that output will go to second fully connected layer, and again sigmoid, and this will be your output. Okay, so everything else remains the same. Only difference is the loss function. Previously, we used mean square error because it was a regression. Now we are using binary cross entropy. If you remember, cross entropy was for any class. Binary cross entropy is for a two class. Since in our case it's a two class problem, that is why we are calling it a binary class entropy loss, binary cross entropy loss. So that's it, the only change. Then you convert all your data into tensors. You run the same for loop. Nothing changed. You first do your forward pass with this. Sorry. You first do your forward pass with this particular call. Then you calculate your loss in the next, and then those three lines for your backward pass. Everything else remains the same. And this is how your loss looks like. You start off with 0.5, you come to 0.2. Even the predictions remain the same way. Okay. So yeah, I'll just stop here. We can discuss more in the next class. But any questions or anything that is unclear in the code or theory, you can ask right now. Sorry, it went a bit beyond time. But all of this, I hope it's clear because it's very important. These are all very fundamental to understanding today's big neural networks, because all of them follow the same principle, even code wise, even theory wise. So please let me know if there is anything that is unclear.
So participants, any questions? Okay, sir. So the Day-5 faculty development program is very informative, and Aveen Dayal sir explained the concepts. Sir started with perceptron concepts and multi-layer perceptron, activation functions and loss functions, and weight updations. After that, gradient descent algorithm, regularization, and PyTorch basics and examples. Sir, I wanted to extend my heartfelt thanks for your insightful presentation in this session, and the practical examples you provided will certainly help us to enhance our knowledge. So thank you, sir. Thank you very much.
Yeah, thank you, ma'am. Thank you.
Thank you. Sir. So dear participants, thank you for joining. And tomorrow the session starts at 7 p.m. sharp. Thank you all.